it's time to start. So first talk of today will be by Wendelin, who will be talking about relative overgeneralization in distributed control. So thank you, Wendelin, for joining us, and over to you.
Hello. So I haven't timed this talk, so we'll see how long it takes. So my name is Wendelin. I did a PhD in Berlin, spent the last 2.5 years in Oxford as a postdoc, and will now soon start as an assistant professor in Delft. The talk is about two things. Like primarily, I want to present you one of the projects that we have in Delft, which is decentralized DC power grids. This is a project we do in collaboration with a startup called DC Opportunities R&D. If you want to have a look here, I hope you all can see my mouse. I hope. Anyway, here's the link.
Yes, we can.
Okay, great, thank you. And the goal of this project is to have like a collaborative multi-agent control system that is able to distributely learn how to control DC grids, which I will explain a little bit more in the coming slide. And the reason why I want to present it here is that we're basically working with something I would call a distributed battery architecture. So all of the things that we're working with will be very familiar to you, but they will basically, we don't have the ability to just decide what the communication structure between the agents will be, because this is given by the hardware. Particularly, I want to highlight 3 particular challenges that we have. All of them have in some way to do with learning the communication between the agents. The first one is neural message passing. So this is actually the weakest of the least explored of the topics I want to talk to today. This is basically how can we learn different nodes to communicate in a graph. The second one is multitask learning. Here, the challenge is that because of energy consumption, our power grid controller cannot learn after it has been deployed. So we need to basically train the entire network with multitask learning such that it can adapt to different topologies and demands on the fly. And the last one is where I will spend the majority of this talk, is about relative overgeneralization, which is the necessity of choosing actions in a coordinated fashion. And this is based on, most of it is based on a ICML paper from this year that I wrote. Okay, let's start. What are DC power grids? So most power grids that we have right now work on alternate current. However, you could also run a power grid in principle on direct current, which has interestingly much better transmission dynamics. Like if here we compare the power that you can actually transmit through a copper cable, and you see basically this on the x-axis you see the length, and on the y-axis you see the amount of power in kilowatts that you can transmit, and you basically see that in the AC regime, we can only transmit like around 3 kilowatt or so over a distance of like 300 meters. Whereas in a DC grid, we can basically transmit factor 10 more, which is like one of the reasons why we want to look into it. However, one of the big challenges in this kind of setup is that a DC grid has no compensation mechanism for stabilizing voltage. Basically, if one of the devices that's connected to the network switches off, the voltage will rise. And to keep the voltage halfway decently stable, you need to switch on another device. That doesn't have to be like a consumption device. It can be like a battery, for example. But you have to do this, otherwise you will fry all your electronics. So so the current drive towards the green energy revolution that we will have to do within this century forces us to radically rethink like how do we think about power grids essentially. Like first of all, we have in the new power grid or the power grid of the future, we will have decentralized energy production and consumption. That means that often the large infrastructures that we are used to that are all based on AC power will no longer be useful in this new world. Secondly, our sources are like the solar and wind power produce like DC power, although, wait a second, wind produces AC power, but solar produces DC power. And we have to deal with new challenges like energy storage in electric cars, which you can imagine just like would drain most of the power in a network if we don't like collaborate between the cars when they will be loaded. For this, we want to develop smart DC devices, and our collaborator is actually working on building these things in real life. You see here, this is an oven that they are working with. And the interesting bit here is that there's no longer an AC-DC conversion necessary because most appliances work with DC power. But on the other hand, we need to find a way to let the devices to communicate with each other so that they can balance out the voltage and so that everything remains safe. Like one of the major applications areas that we see for this is actually third world countries. Here we often have like villages that are not connected to any national grid and which need like a do-it-yourself solution where they can have communal power generation and communal power consumption. And we think that these DC grids would be an ideal application for this kind of situation. So, as I said in the beginning, we want to apply multi-agent control to this. So basically what we do is we interpret this, this local grid, like basically like all of the connected components that produce or consume or store energy as a grid where the nodes are sinks, sources, and batteries. We want to model the control of these power systems with multi-agent reinforcement learning by interpreting like each device as an agent and by interpreting the problem as a collaborative problem between all the agents. So all the agents want to maximize their reward, which is defined as keeping the voltage stable while fulfilling the demands of all of the devices that are connected. Interestingly, because we already have a cable connection structure in place, we can actually use the power cables themselves for communication. You can like transmit around like 10 kilobyte per second or so between those. And if need be, we can also like use special cables that are basically have a separate data channel. The interesting bit, like if you're looking at this, is that it will probably remind you a lot of the Badger architecture, because, and these are like now 4 points that I want to explain in detail in the following slides. First, each device is basically an agent that estimates a Q value, and it estimates the Q value for switching on and off specific components of this device. Secondly, each device is represented internally as a recurrent neural network, and these nodes in the graph are continuously exchanging messages to exchange, like basically to agree on a interesting local subset of the state. Thirdly, one of our big challenges here is a multitask challenge, because after we deploy the control, we cannot learn anything anymore. This is because like learning is a very energy intensive process, and we can't do this on like cheap electronics. And fourth, which is like the major component of this talk and will take like probably half of the time, the actions need to be coordinated. And this is pretty easy to see. Like if you would imagine, that each of those devices has a Q value for switching on and a Q value for switching off, then if some of the, like one of the devices goes offline, another one has to switch on. So, but if even if the communication is good in like moving around, or the information of like what's the situation, there's still sort of like symmetry breaking necessary to make sure that you can actually like one device switches on and not 10 devices determining randomly whether or not they want to switch on. So let's start with the first one, and this is just basic. Let's just define like multi-agent reinforcement learning. So basically, it's just like reinforcement learning. Like formally speaking, we just use a DECPOM-DP, which is a decentralized, partially observable Markov decision process. Here we have like n agents, like these little fellas here, and they share a collaborative reward. This is important. We don't have per agent rewards, but like every agent gets to see the same reward, and that's the team reward that everybody wants to jointly maximize. Every agent interacts with actions with the environment and gets observations back. There is a state of the system, but often we assume that it's not visible, except maybe during training. We'll talk about it a little bit later. The thing that the agent basically has access to, and that is all that they see, is the individual observation action history. This is just the history of all the observations and actions that the agent has seen so far in this episode. And the challenge is that we have this joint action space, which is just like the actions of all the agents in a large vector. And this action space grows exponentially, which is like one of the biggest challenges in multi-agent reinforcement learning. We'll use a framework called centralized training and decentralized execution. Here, we basically define a joint Q value in which basically encompasses, or like which computes the value with respect to all of the agents' observations, tau, and all of the agent's actions. This is just like the standard definition of the optimal Q value. This is what we use in the experiments later. We just use variations of Q learning. And importantly, what we're doing as well is we compute, we represent these value functions with neural networks, which are based on RNN history. So what we're effectively doing is we're taking the observations O and the actions A of each agent. Oops, that's not here. And the previous hidden state, and we run it through an RNN to get the next hidden state. Each agent has their own like belief or hidden state, and our value is based on all of the beliefs and all of the actions. We'll separate this in a second. So in practice, what we want to use is a formalization called graph neural networks. Graph neural networks are essentially assuming that you have the global state as a graph, which is annotated in many ways. And this graph basically has a set of nodes which correspond to devices or agents in our case. And it has a set of edges over which it can communicate. In this case, the cables between the devices will be the edges that we will communicate over. I'm showing here an agent-centric value decomposition. Put a pin in this for now because we will actually return to this in a couple of slides. This is like one of the major issues that we have when we want to coordinate actions. But like for now, just assume we are using this kind of value decomposition where we take like our joint Q value and we represent it as a sum over so-called utility functions. Each utility function is just depends on one agent's hidden state and one agent's action, because this allows us to decentralized decide which actions to take by in just like every agent can maximize their own utilities or choose the actions that maximizes their own utilities. But like in difference to before, what we see here now is that the hidden state takes all the stuff that it did before, but now it takes also a summarized message. So this message basically is computed by a continuing process of message passing and aggregation. Messages are generated, are sent from agent J to agent I at time t by just like running a neural network that takes the hidden state at time t-1, all of the other inputs that you need to compute this hidden state except for the joint message, and the message that you have received from agent I. This is important to break symmetry later. And we have an aggregation function which takes all the messages that arrive at node I and kind of combine them in some way. The classical version here, the classical aggregation function here is the sum. However, that has some issues, and in some experiments that I can't go into detail here, we found that using the sum here has large problems transmitting information, or like directed information over large distances, which we need to do here. So this is like something, sorry, please.
Yeah, short clarification. I'm just wondering, the function for the message from node J to I, does it really have as input the output I and action I, or should it be J?
You're right, it's J. Good, clarification. These two indexes here should be J. If you have any questions or any comments, if I make typos, please let me know. Okay.
And maybe my question, so the mu is actually the message that's being sent, right? That's the aggregated message.
So mu ji is the message that's sent, and bar mu I is the aggregated message that's then later used to update the RNN.
Okay, thank you.
So
one more question.
Yes, please.
So the theta and the phi, they are global parameters. There shouldn't be an I at all of them.
Yeah, so basically this is something I will go a little bit more into later when I talk about deep coordination graphs, but you could imagine it the following. You could think that every utility function, like every agent has a unique utility function, and every agent learns their own utility function. However, since we are already conditioning on the hidden state of an agent, and the hidden state could in principle contain something like an identifier that identifies each agent uniquely, or identifies the class or the role that the agent will take, we actually don't have to have like unique neural network for each agent. We can use the same theta, the same parameters of the model, and let just like the current belief of the agent differentiate the behavior. And the same holds actually for the RNN.
So you share the parameters.
Yes, in practice, we will share these parameters. This is like in graph neural networks, this is important because you want to be able to change the topology on the fly. And that is not possible if you have like specific neural networks assigned to specific nodes or edges in the graph. So, but I'll talk a little bit more about this later in a different setting. Okay, so basically the idea here is that just this type of structure, which should be very familiar to all of you, should be able to generalize over different topologies, and therefore we can just train this end-to-end with backpropagation through time, and then the GNN will a suitable communication protocol will emerge. That is the hope. We haven't really run too many experiments with this yet, so I can't say how well this works in practice. So the next thing that we have to talk about is multitask learning. The problem here is that both the grid, the grid architecture and the demand can change during the execution time. The problem is that if you have if our little helper here comes and just connects a new device to the grid, then all of a sudden the topology changes. And at the same time, this device often wants something, like you connect your phone to the grid to load it. So all of a sudden the demand changes as well. And retraining all of this would take a lot of time and energy. So we want to have something, we want to have one policy that's able to deal with all tasks. The first thing we already talked a little bit about is parameter sharing. Parameter sharing should be able to generalize. However, there is still a large question mark here, and that is if you train on one task why do you, like, even if your inductive bias, or like the structure of your networks, allows you to generalize in principle to another task, why do you believe that training on one task would help you here? Maybe you just overfit everything to this one task and then it doesn't generalize at all. And to kind of make this more visible, what we will do is basically we will use some kind of domain randomization, where we are training on a distribution of tasks, and each episode is trained on a different task. Or if we have a continuous running of the network, then we would just, like, at random intervals change the demands and the topology of the network. This is actually possible because we can simulate what happens in these networks quite well. The thing that we cannot simulate well, but what we can, like, infer from real data is when which kind of devices go online and what these devices need. So what we can actually do is we can generate random topologies, and then let each device in these random topologies pick, like, a random data source that makes sense, like that's appropriate for the like time of the day and the time of the week and all of that, and then simulate with this network. Next episode, reshuffle everything, and that should work. To give you an idea, what I mean by that is, I wanted to show you, like, a nice little paper that we currently have under review in Europe, which is AI QMix. Here we are playing StarCraft, and in StarCraft, the observations are essentially a list of environmental objects. For example, like the players and the enemy's units, that an agent, which is like every unit in this like every of the player units is an agent, and you can like every unit basically observes a list of objects. These objects can be summarized by using a self-attention network, which we then dubbed AQMix. And this allows to run the same policy on a set of varying numbers of objects. So basically, we can create a distribution of tasks. In this case, a distribution of symmetric games where both teams get the same type of units and the same amount of units. But the amount and type of units is varied between 2 and 8 zealots or stalkers, which are like these these two types of units in the game. And sorry, you see here, like the mean pool QMix is like one of the the standard ways of like dealing with this situation, with this like list of units. And it works really badly if we add like the attention layer to it. Then all of a sudden the performance grows quite a bit. Interestingly, this is both for QMix and VDN. QMix is the current state of the art on StarCraft, and VDN is a simplified version that I will talk about that in a little bit more about. However, this is like all of this is basically we are training on a randomly drawn set of tasks. So we will see a lot of different tasks. However, you can go farther than that because you can actually imagining subtasks being executed. So what we do next is we have an auxiliary task. And in this auxiliary task, we imagine a new subtask by splitting the objects that we can see into groups. Like we started with 2 groups, but you can actually extend this to an arbitrary amount of groups. So you split them into 2 groups. Then you compute the utilities for each of those groups under the assumption that they cannot see the other group. So basically, this is a smaller subproblem that you could solve. And then we take basically those 2 utilities and mix them together with a hypernetwork. This is the standard way that QMix actually operates. So this is just like a straightforward extension of QMix. And as we can see, using these imagined tasks during training actually improves our AI QMix from the orange line to the blue line. So we generalize way better and we learn much faster because we can actually imagining like subsets of tasks. And that would be like a nice thing to do in our grid world as well, but we'll see about that. So the next thing I want to talk about is actually the major issue of this talk. So I've kind of mentioned before that we will use that we're using some sort of factorization, and I really have to speed up, otherwise I will not be able to talk about all of these things. So basically what we have seen before is we use these agent-centric factorization of the joint value function. So basically what we do is we take our joint value functions. We say like, okay, each of those agents is like a unique node. And for each of the nodes, we add like one so-called utility function that computes the actions for that node, or like the utility of the action of that node. And our joint value function is then just the sum of those. This is called a value decomposition network. This is the citation, and has the advantage that you can actually decentralize the entire control process, because what you can do is basically every agent just has to know its own utility function, and then can maximize its own utility function to choose the best action at each point in time. However, this on the one hand is able to reduce the exponentially growing action space to like something sensible. But the downside is that you reduce the representational capacity of the joint value function. And this can lead to something which is called relative overgeneralization. And that will be the major focus of the rest of the talk. So what do I mean by, what is relative overgeneralization? I want to show this at a simple example. This is an example that we actually implemented. The code is available here over this GitHub page. So basically what we have here is we have a grid world, and we have a set of predators which are hunting a randomly moving prey. And the prey is just randomly moving around. It's not fleeing from anything. It's just like from all of the possible next states that it could move into, it just picks one randomly. Now, because we are using the VDN decomposition, where we basically say the value is like the sum of the utilities of our two agents, we can actually look at like what is the theoretical expectation of the first agent's utility. And this is simply, you're looking at the first agent's utility is just like the utility for choosing an action in a state. The superscripts here always indicate the agent, the subscripts always indicate like time steps or something like that. And in reality, this is like, it depends on the Q value of the value function in the future and so forth. But like for simplicity, let's just assume that it only depends on the immediate reward. And then you can basically see that the utility of the first agent is the joint reward, or the reward that you get for the joint actions, and in expectation over what the other agent is doing. So it depends on the second agent's policy, which at least in the beginning is usually epsilon greedy, so it's random. So now, if the prey cannot be caught alone, so if you have like two agents which are standing next to the prey, they can execute a specific catch action, and if they both execute or choose the catch action, then they will get a reward. So the utility of the first agent for the catch action is simply the reward times the probability that the other agent will choose the catch action in the same situation. As you can see, because there's no punishment involved, as long as the second agent sometimes executes the catch action, the utility is positive. Therefore, VDN can learn this without a problem. You'll see it in a second. However, now we introduce a punishment. Like we basically say, if we are in a situation where both of the agents could, in principle, capture the animal, but one of the agents decides to do something else, and only one of the agents is executing the catch action, then we give a small punishment for that case. So now if we're looking at the utility, it's like the reward from before minus some punishment times the probability of choosing anything but catch for the other agent. So if this term here becomes larger than that term, the utility drops below 0. And since there's nothing else is rewarded or punished, the agent will never choose the catch action because the catch action actually looks worse than doing anything else. This is called the relative overgeneralization pathology. And we can see it by just running exactly this experiment here with different amounts of punishment. Like in the first line, we see if we have no punishment, then VDN, our VDN decomposition, is just like deep Q learning with a VDN decomposition of the Q value function. It just learns the optimal policy pretty good. So the dashed line here is actually the maximum amount of reward that you can get in this environment. But as soon as we increase the punishment, we see that the performance drops like massively. And until like a punishment of -1.5 or so, we don't see like none of the agents, like none of the seeds that we run is actually able to solve any of this. So this is a big problem. What can we do about it? Well, the major issue here is that, or the major problem here is one of representation. The problem is that we cannot represent the joint action between the two agents. However, if we would just like roll this back and just say, okay, then let's just use no factorization. Let's just use a function which, like an arbitrary neural network with so many actions. Then we would have the representational capacity, but on the other hand, everything like training would run really, really slowly because you have to generalize over like a huge space. Maximization is no longer possible in an analytic fashion. And I had like lots of problems with this approach. What we actually want is we want to have like an ideal factorization which encompass to model some of the joint actions, but not all of the joint actions. And in fact, there is a method to do that, which is called a coordination graph. So in a coordination graph, pretty much as before, we have nodes which represent agents. And then we have just like a set of edges which we add to that. This can be an arbitrary set for now. And each edge induces a so-called payoff function which depends on both actions, like the actions of both connected agents. So that our joint Q value then is just like the sum of the payoffs. The advantage of this is that it's very flexible. You can, for example, you could induce or introduce hyperedges which connect more than two agents, and you would be able to get like degree 3 coordinations and so forth and so forth. The other big advantage is that you can use tricks or algorithms from belief propagation to do message passing on these graphs. Basically, the nodes will exchange messages over the edges, and you can actually show that in at least like under some assumptions, like in a tree structure, for example, you can compute like the actions that would maximize this entire graph after a couple of message exchanges. This means that we can now distribute our, this means to some degree that we can distribute the policy. It's still like a difference to before when we had like fully decentralized policies. These or the greedy policies based on these coordination graphs can be distributed in the sense that you only need to communicate with your neighbors to determine like the globally best solution. And what we use here in practice is this formulation where we actually combining utilities and payoffs. We are restricting ourselves here to like classical edges that just connect two agents, but you could extend this equally to like larger things. There is an interesting subcase here is if you make the set of edges empty, then this just reduces to standard VDN, which is a nice case. And we can train it, like we can use all like neural networks on all of these, and we can train it with DQN. However, the amount of neural networks, if we don't use any kind of parameter sharing, is just like grows very, very quickly. And so far, these coordination graphs were only able to solve like non-sequential tasks here in this paper. So to extend this like to sequential tasks, or like to real, the tasks that we are interested in, we introduced like the deep coordination graph, and I will just like speed through this a little bit. So basically what we do here is we use 5 tricks deep learning to make this problem feasible. Like the first one is we take like the definition from before, where like these are neural networks, no parameter sharing, nothing. So the first thing is we restrict the inputs, which in principle could just be the entire state of the system, to the locally available information that's necessary for us. The second step is we share parameters over an RNN. This is basically the same type of RNN that you have seen before. It's just like now that the edges here, they depend on the observations of both agents, and we no longer have to keep like a different neural network for each payoff and each utility. We can just like generalize over them as we did before. Third one, and this is a little bit crazy, we did a low rank approximation. So the issue here is that during message passing, you have to compute basically this matrix here. So you have this, you have this like a function which gives you an output of action of agent I times action of agent J many outputs. And this turned out to be really problematic to compute with a deep neural network approach, because there's so many of these, like you're only getting like a gradient signal for the action combination that you have actually chosen. And there's so many other action combinations which are unchosen for a long time. And we kind of solved this problem by using decomposition, which is very similar to singular value decomposition, where you can just take any matrix and you can decompose it into the outer product of vectors, like basically of the eigenvectors of the system or the singular vectors of the system. And here we just like say, okay, these vectors here are produced by functions. The red vectors by this function and the green vectors by that function. And we just sum over the outer product of those. And this allows us to like spread the gradients much wider, and it worked wonders in like harder tasks. Last thing, or second to last thing like this, we wanted this to be permutation invariant. This is important because like basically we wanted to be able to apply the same function on a network with permuted nodes. So we just like compute our payoffs, which have an order. We just compute them backwards and forwards and then take the average between both. And lastly, in some situations, we have privileged information available during training, but not during execution. And we can actually, we integrated this here by just like adding a state-dependent bias. So this is basically the basic of this paper, of our last paper in ICML. Like if we are applying this now to the task, the relative overgeneralization task that we talked about, we see that if there's no punishment, there's no relative overgeneralization, and we just work as well as VDN. So we're like as sample efficient as VDN. If we increase the punishment, VDN fails, but our model consistently solves it. This is so. If we compare this now with a coordination graph which has no parameter sharing, this is the magenta line here. We basically see that. Oops. We basically see that just introducing so many neural networks just like makes the entire problem very hard to learn. Like even without any punishment. It takes forever to learn. And then if we increase the punishment, like it's barely noticeable that we learn at all. In comparison to other methods, we basically see that only like benchmark methods that do have a fully joint value function can actually solve this problem. Like the green line here is Qtron, which is actually an actor critic model that has like a fully represented joint critic. And this here is low rank Q, like the gray thing is low rank Q value. This is another benchmark. We also looked into topologies and saw that actually like fully connected topologies work the best in comparison to all of these other topologies that we looked into. We believe that this is primarily due to representation capacity, but this is still like a somewhat unclear, like unsolved issue will look, particularly since we cannot choose the topology in our power grids that we're envisioning. There's another thing, like if we now introduce these low rank approximations that I talked about, like the red line here is still for without any low rank approximation. But if we introduce this, then like basically all like of the low ranks solve the problem much faster with like almost no no drop off in performance. So basically can increase our the advantage of our method, even like double the advantage of our method basically in comparison to alternatives. There is also something about StarCraft, but I will drop it. So in the interest of time, the last question that I wanted to ask here, that's not yet, so that's not in the paper, that's like new stuff, is it's cool to have like these DCG policies, but they still need a lot of message passes through the graph, and this might be prohibitive if we have like communication constraints. Like we can't really we can't squeeze that much data through our power cables. So one interesting observation is that any greedy policy is always decentralizable. That's because if I have like a joint greedy policy, I can always write it as a product of like individual greedy policies. And we just make the leap of faith here that the same holds if you reduce like the observations from like the full state to like just the individually observable states. So one simple idea would be just to say, okay, if the greedy policies, like if DCG always has a greedy policy and the greedy policy is always decentralizable, why don't we just use classification to predict the greedy policy? So this is what I did here. I'm just using a standard cross entropy loss here, where I'm computing these these bar A of actions are like the ones that maximize my joint Q value, and I'm just trying to find like a decentralized policy like here that predicts these actions. However, so this works to some degree, but it's very slow. I'm not entirely certain why. I think this is because in the beginning, the policy is very different from the end, and there's no like gradual way to shift you around. So you kind of overcommit in the beginning, and then later it just takes forever to correct that. So an alternative to that is you could also think about this as, you could also just like compute the policy gradient. So if you're familiar with policy gradient algorithms, this is not exactly what a policy gradient normally does. Normally, this Q value here in the policy would be the critic of that policy. But here we just say, okay, we already have a perfect Q value. We just want to find like a policy that maximizes this Q value. However, empirically, this is complete garbage. Like this is the cyan line here, and it just like goes up and down. There seems to be no learning progress. So I sat down and thought a little bit about like, why is that? If we need to just try to optimize that, like why don't we get like a, why don't we learn anything with this? And you can actually see why if you're looking into the gradient itself. So this is the gradient of the expected policy gradient loss function. You basically just see that the gradient just walks through the, this is like basically the expectation, so it just walks through the expectation. And next thing is you, because this is a factored policy, you can actually reformulate it as a sum over terms that only depend on agent I. Then this is just like the sum over all the actions of agent I, the gradient over, like the gradient over its policy. And then like this large term here, which I dubbed QI. And this QI is just basically the value function where you marginalized out all the actions with respect to the policies of the other agents. And you see from this definition here that the policy gradient with a factorized policy suffers from relative overgeneralization. Exactly for the same reason that we had in the simple predator-prey example that I had before. If these guys here are doing something random, then, and I get a punishment every time that they are doing something random, then the average punishment can outweigh the reward. So what can we do about this? And the solution for this is actually quite simple. We can actually just compute the same function qi, but for greedy actions. So just like instead of sampling those actions here from the other policies, we can just like replace this with the greedy action that we get from our joint DCG Q value. And that now solves the problem. The blue line here shows basically there's still some comeuppance in the beginning, which is like that you're overcommitting to the wrong policy, which is the policy which does everything but the right thing. But then after a short while, you basically you learn the problem and you learn it almost as good as the DCG factorization, and like significantly better than the next best method on this data set, which is Qtran. This is like one side note here is I was really surprised when I saw this, because this policy factorization is the standard approach in actor-critic algorithms that deal with continuous action spaces. So like every actor-critic algorithm that deals with discrete action with continuous action spaces has these factorized policies just between the different action dimensions. And I was like sort of, it's baffling to me that we never see this issue come up anywhere. So I'm not sure about that. Maybe the tasks, like the tasks that we are currently looking at in this domain, simply don't show any relative overgeneralization issues, or I don't know. So in conclusion, what I wanted to show you was like, we're working on this neat power grid problem, which is a sort of a distributed batch approach. So like just to correlate these, so we're talking about agent or devices, which are like sources, sinks, or batteries for power. The connectivity in like, which is normally in Badger, is like a design decision. Here is given as learned communication over the power cables. The power cable topology is fixed. The inner loop in Badger would correspond to a distributed policy that controls the power grid and just tries to keep it stable, whereas the outer loop is training on randomized topologies with randomized data to make sure that you're actually can adapt it to all of these different demands. However, we're facing two obstacles here. The first obstacle was like given as number 2 in my previous list. That's that the devices need to agree on a global state. This is really important because the devices, like to decide whether or not you should switch on or off, you have to know what your environment needs. And therefore you have to communicate with each other, like who needs the power the most right now. However, this has an issue. Like we can use this with graph neural networks, but in all previous experiments, it turned out that message passing is actually quite hard to learn. I've also heard the same thing about from the Badger community. And secondly, the bandwidth that we have is limited, so we'll have to see how well this works in practice. The second problem is what I had as problem number 4 on my previous list. That is that the devices need to agree on a joint action. Here, the biggest problem is that if I switch on like a device on or off, then only one other device should react to that. Or like only 1 or 2 other devices should react to that, but I don't want to have like a random decision from everybody. And like we will want to look into DCG to solve this. This has the huge advantage that the message passing doesn't have to be learned. like all of the message passing is from belief propagation and it's fixed and it works. And it has a second big advantage that we can actually decentralize. During the training, we can actually train a decentralized controller on the side, which is able to solve this without doing any message passing. That's my talk. I have a lot of other things like references here if you are interested in that. Thank you very much for listening. Please ask questions.